All right, so we can summarize it like this. Dalton's law, the total pressure here, 1 atmosphere, is equal to the sum of the partial pressures. So the partial pressure of nitrogen is 0.8 atmospheres, of oxygen is 0.2 atmospheres. And so we have that. There's a restriction here, though, and the restriction here is this. V total is equal to V1, which is equal to V2, which is equal to V3. And so the total volume is going to be the same as the volume for gas 1, the volume for gas 2, gas 3. So this is why if I have 100 liters of air, and air consists of nitrogen and oxygen, how many liters of nitrogen do I have? I have 100 liters. How many liters of oxygen do I have? 100 liters. If you go on to Avogadro's, Avogadro says V total is equal to V, the partial volume. So the V total here is 100 liters. 100 liters, oops, what did I do? I made a mistake here, sorry. It's not 0.8 liters, it should be 80 liters. And so the 100 liters of air is going to consist of 80 liters of nitrogen and 20 liters of oxygen. And so the 100 liters of air, which is our V total, is equal to the volume of nitrogen, 80 liters, plus the volume of oxygen, 20 liters. If there's a gas 3, we'd add that in there as well. But the weird thing about what happens with the pressure, for example, the pressure of the air here, which is 1 atmosphere, will be equal to the pressure of the nitrogen, which is equal to the pressure of the oxygen. So all the pressures are the same. So the pressure of the air is equal to the pressure of the nitrogen, which is equal to the pressure of oxygen. Oops, I need to do this generically, sorry. Generically, nitrogen's gas 1, oxygen's gas 2, etc. And so for Dalton's, we call this constant volume. For Avogadro's, we call it constant pressure. Both are going to be like 20-80 or 80-20 split. A scientist sets up an artificial atmosphere with 4 gases. Their partial pressures are 0.78 bars of nitrogen, 0.21 bars of oxygen, 0.009 bars of argon, and 0.025 bars of water. What is the total pressure? Are we at constant pressure? No. Well, all the gases have different pressures. Therefore, all we do is we add them up. So we just added up 0.78 bars of nitrogen plus 0.21 bars of oxygen plus 0.009 bars of argon plus 0.025 bars of water. Add those up, and how many bar total do we end up with? 1.02 bars. 0.02 bars. Any questions? They didn't give us the volume, but we know whatever the volume is, the volume of this artificial atmosphere is equal to the volume of nitrogen, which is equal to the volume of oxygen, etc. I don't really like this figure here that much. It's supposed to be an illustration of Dalton's. So for example, the nitrogen here is at 186 millimeters mercury. They call it a 1 liter flask. And so how many liters of nitrogen do I have? I have 1 liter. And then the oxygen is in a 1 liter flask. So how many liters of oxygen do I have? 1 liter. but it's 93 millimeters of mercury, which is less pressure. How many liters of mixture do I have? So what they do is they just put it all into one container. It's 1 liter plus 1 liter gives us not 2 liters, but 1 liter plus 1 liter gives us 1 liter because we're just squeezing it into one container. And so this is an example of Dalton's. And so all we do to figure out the pressure is you take the pressure of the nitrogen plus the pressure of the oxygen. This should give us the pressure of the mixture. Just here. But the reason I don't like this is because, is this really the same volume? Are these all the same? No, because look at the level. You know, this one's going to have the biggest volume. And this one has the smallest, and this one has some intermediate volume because the level here is going to change the total volume of the flask. So that's why I don't really like this. This is showing they're taking KClO3. You know, what's the KClO3 called? Potassium chlorate. Now, potassium chlorate is not so stable when it's heated up. You know, when it's heated, you have to watch out because chlorate's potentially dangerous, but skip the intro here. I'm going to skip ahead. So this some potassium chlorate, it's white powder. I usually have it in the angle. So they're heating up the potassium chlorate, and then what happens with the potassium chlorate is it starts to decompose. Not such a dramatic decomposition. It's much faster if you have a catalyst in there. That was quite a slow decomposition there. It's white, but if we add some black catalyst in there, it's manganese. See, this is with catalyst. So they added just a little bit, a quarter gram of MnO2 to help speed up this reaction. And they end up putting some food color here. But what's going to happen is the KClO3 decomposes and produces oxygen gas. That oxygen gas, if we want to track, so here it's starting to decompose, it's going to start bubbling. And the oxygen gas is going to fill up this flask here with oxygen. As it fills up this flask with oxygen, it pushes the water out here. So the oxygen's coming in here, pushing against the top of the liquid, and the top of the liquid is exiting out this tube here, cylinder up here. So let's take a look at the reaction here. The redox reaction. KClO3, which is a solid, decomposes. When it decomposes, it forms oxygen gas. And do you know what the other product is? It turns out the other product is KCl. So we'll end up forming 3 halves oxygen. KCl is a solid. So we'll just double everything. So we end up with 2 KClO3 solid goes to 2 KCl solid plus 3 O2 gas. And so we should be bubbling off pure oxygen gas. But what we collect in this flask is not pure oxygen gas. You know what it is? It's contaminated oxygen gas. What is it contaminated by? So here they're showing it in this apparatus here. They're generating the oxygen gas, which is going to bubble up through here. They're going to trap it in this inverted tube here. Do you see that? But this reaction is only producing oxygen. KCl is going to stay here. This oxygen is contaminated. Do you know what it's contaminated by? Let's say there's no air. We can get rid of the air in the system. Even if we got rid of the air, it's still going to be contaminated. Do you know what's going to be contaminated by? Hydrogen. Not hydrogen. It's something that contains hydrogen. Water. It's going to be contaminated by water. Well, it doesn't seem like it's contaminated by water. I mean, the oxygen's up here and the water is down here. But it's contaminated by humidity. The water evaporates and will humidify the oxygen. That's basically it. This is like an indoor swimming pool. The air inside an indoor swimming pool is very humid. That's because the air inside an indoor swimming pool has been saturated with water vapor. Well, the oxygen here is going to be saturated by water vapor here. So we need to talk about that. So whenever we collect the gas over water, that gas is going to be humidified. And if there's enough time and there's plenty of water, it's going to be 100% saturated. Now 100% saturated depends on the temperature. The higher the temperature, the more water evaporates and the more humid the air can become. At lower temperatures, the less water evaporates and the less humid. But it doesn't matter what the temperature is, as long as this has been sealed here, it's going to be 100% relative humidity inside that container. In this room, is it 100% relative humidity? No. 100% relative humidity is very uncomfortable. But inside, if you're trapped inside this container, it would be 100% relative humidity. It would be very humid and uncomfortable. That's what the oxygen is doing. And so it turns out that the total pressure inside this tube is equal to the pressure of the gas plus the pressure of the H2O. Now what they're doing here is that they're getting the water levels to equalize. What that means is the weight on the water outside is exactly the same as the weight on the water inside. If the two weights are equal, then what we can say is that the pressure inside here is equal to the pressure outside here because it's balanced. And so the barometric pressure, which is the pressure outside, or the P total, is equal to the pressure of the gas plus the pressure of the water. Now, 100% relative humidity only depends on the temperature. It doesn't depend on the size of the room. And so the percentage of water molecules just depends on the temperature. If I make this tube bigger, then more water molecules can evaporate, but it'll still give me the same percentage as far as the humidity goes. That's 100%. And so typically what we do is we use the partial pressure of water out of a table. This would be like a humidity table. Let's take a look. It's called the partial pressure of water. Or the vapor pressure of water. Probably more commonly called the vapor pressure of water, because this is when water evaporates, how much humidity does it create. So these would all be saturated at 100% relative humidity. So let's say we're at 25 degrees C, then we're going to get just 3.2 kilopascals worth of water vapor there. Kilopascals. Kilopascals is one of those European units. So maybe let's try some US style units. PSI. The millimeters of mercury. This is probably better here. And so at 25 degrees Celsius, then we're going to just generate 23.8 millimeters of mercury pressure just from water collisions. So if the size is bigger, it still generates the same pressure, so we've got to evaporate more molecules. If the size is smaller, the pressure stays the same. It just depends on the temperature. And so we can get the pressure of the water based on this, the vapor pressure data, water. So we can try this example. Calculate the partial pressure of oxygen in atmospheres in a sample collected over water. Well, any gas sample that's collected over water will be 100% humid. This is what happens. So, you know, if I brought in a big pool of water in here and let that water evaporate, eventually we'll hit 100% relative humidity. Eventually, that's going to depend on the temperature. So given that the total pressure of the mixture is 0.98 atmospheres and the partial pressure of water vapor is 16.5 millimeters of mercury. And so the 16.5 millimeters of mercury that comes from the table, 0.98 atmospheres they measured. And so they want to figure out how many atmospheres or of oxygen. So this number comes from a table, 16.5 millimeters of mercury. So that's the partial pressure of water vapor in atmospheres, or the vapor pressure in atmosphere. So 16.5 millimeters converted to atmospheres, we get 0.0217 atmospheres. Now the total pressure is going to be the pressure of the oxygen plus the pressure of the water that's contaminating the oxygen, humidity. Therefore, if we solve just for the pressure of the oxygen, the pressure of oxygen is going to equal the total pressure minus the pressure of water. It's the total pressure minus the pressure of water. Comes out 0.96 atmosphere. All right, let's think about this here. about this problem, I think like this, the container. I'll have some container here. And there's water here. I collect my oxygen gas in here. So how much oxygen did I collect? I collected 0.96 atmospheres of oxygen, O2. But this oxygen is not pure because what's going to happen to the water pool? It's going to evaporate. Water evaporates. As the water evaporates, this is what happens. Water evaporates, I get water molecules in the gaseous state, the humidity. This. So as the water evaporates, I'm going to generate water molecules in the gaseous state, humidity. And so this up arrow represents evaporation or vaporization. But the opposite process can happen too, where a water molecule in the gaseous state can come back down and stick to the surface here of the liquid. And if that happens, it's called condensation. So, like this. Now, if the air is dry, then there's not much water vapor in there. And so net, we're going to have evaporation occur, and then it'll become more humid. But there's a limit to what the humidity can be. And so what happens here is we'll have net evaporation, but as we build up more and more molecules in the gaseous state, then we're going to have more condensation. Eventually we're going to hit this point of what we call a dynamic equilibrium, where the evaporation rate is equal to the condensation rate. And then we know we've saturated it. Let's see if I have that. So what happens here is this. When we're at 100% relative humidity, this starts off kind of dry, the oxygen, but more and more oxygen gets water gets vaporized. And so we have net evaporation or net vaporization, but once we get a high enough concentration of water molecules, then we'll have condensation occur. And what happens is once the condensation rate has matched the evaporation rate, then there's no further change. And so when we have 100% relative humidity, there's no further change because the rate of evaporation, how fast it's evaporating, is equal to the rate of condensation, how fast it's condensing. That's what we might mean by 100% relative humidity. Now, we can change the evaporation rate by changing the temperature. The lower the temperature, the less evaporation. The higher the temperature, the more evaporation. So the humidity level can change depending on the temperature, even at 100%. So it's always going to stay 100%, but the amount of water you can put varies depending on the temperature. What that target is, 100% changes. And so in this case, what is the temperature? Well, the temperature is some temperature that causes the water vapor to be at 16.5 millimeters. And so when I look at the pressure of the water vapor, I'm at 16.5 millimeters Hg for the H2O gas. Then I'm going to convert that into atmospheres. Well, that turns out to equal 0.0217 atmospheres of H2O gas. And so now I have a mixture. I have a mixture that contains 0.96 atmospheres of oxygen and 0.0217 atmospheres of H2O. So what is the total pressure? The total pressure is, oops, do I have that right? Yeah. The total pressure is 0.98 atmosphere. P total equals 0.98 atmosphere. So this is an example of Dalton's or Avogadro's? Dalton. All right, comparison of properties of liquids and properties of gases. So just some physical characteristics. Gases can be compressed, liquids cannot. The reason is gases have a lot of empty space, so you can compress them, get rid of some of that, or expand them, increase some of that empty space. Whereas liquids, the molecules are touching here. And so for liquids, you can't really compress them. Gases expand to fill the containers, liquids do not. You know, liquids will just sink to the bottom. Gases will cover the whole container, fill the whole container. Gases have low density, liquids have relatively high density. So the gas here, since it's mostly empty space, density is about 1,000 times less than liquid water. And the liquid water is about 1 gram per milliliter. The gaseous order vapor here is about 0.001 grams per milliliter. Because we end up having 1,000 times more empty space. Gases may be mixed in a fixed volume, liquids cannot. So if I took 100 liters plus 100 liters, I can get 100 liters. But if I took 100 liters of liquid plus 100 liters of liquid, it's not going to add up to 100 liters. It's got to add up to more. Okay, gases may be mixed in a fixed volume. That is, you can put all the gases into one container. Liquids cannot. Gases exert constant pressure on the walls of the container uniformly in all directions. Pressure in the liquid increases with increasing depth. Yeah. So here the pressure is pretty uniform throughout all surfaces here, but the liquid at the bottom is going to be the most dense. All right, now we're going to transition more into liquids. And here are some properties. Vapor pressure is a property. Vapor pressure is the pressure that's generated due to evaporation. So you have to have enough liquid to completely saturate the gas above it. Like in this room, there's not enough liquid here to saturate it, so it's not at 100% humidity. But when we capture gases over water, it will be like this. So this is called an equilibrium process, or dynamic equilibrium, or the equilibrium, more specifically, equilibrium vapor pressure here. Equilibrium being 100% relative humidity. Here's the evaporation process, condensation process. All right, that's called the vapor pressure. So, depends on the temperature here. I'm going to have fixed pressure of water here. If I increase the temperature here, we'll raise the vapor pressure. If I decrease the temperature here, it'll lower the vapor pressure. Some other properties that we're interested in is the heat of vaporization. Heat of vaporization is how much energy does it take to vaporize. Then we have the boiling point. The boiling point is the temperature at which the vapor pressure becomes equal to the pressure above the liquid. So let me show you this table here. So this is the vapor pressure of water. So at low temperatures, not much evaporates. We have low vapor pressure. As we increase the temperature, more and more evaporates until we hit 100 degrees C. At 100 degrees C, what is the vapor pressure? 760. 760 millimeters of mercury is the same thing as 1 atm. And so this is normal pressure. So this is kind of interesting because normal pressure is pushing down, and then we have the vapor pressure kind of pushing up. And so when the atmospheric pressure and the vapor pressure is this here. When the atmospheric pressure and the vapor pressure match, then we have boiling. The liquid can boil, that is spontaneously vaporized like that. And so that happens at 100 degrees C here when the vapor pressure is 760. So 1 atmosphere of water boils at 100 degrees C. The vapor pressure and the atmospheric pressure are equal and opposite. A couple of more properties of liquids. One is viscosity. Viscosity is the resistance to flow. And the last one is surface tension. So something that's very viscous would be like maple syrup. Maple syrup has high viscosity, that is high resistance to flow. And then surface tension is how much energy it does take to break the surface of the liquid. Surface tension. All these properties are related to what we call intermolecular attractions. Intermolecular attractions. Intermolecular attractions are what holds the water molecules together. So we're going to look at those now. All right. Oops. So in a water droplet like this, is gravity holding the water molecules together? If you have a water droplet, does gravity hold the water molecules together? It's not gravity that's holding them together. You know what's holding them together? The water molecules are being held together by intermolecular attractions. The intermolecular attractions are kind of like this sticky stuff. And that stickiness is generated by electrical forces. Waters have a positive end and a negative end. They're polar molecules. And those dipoles, the molecular dipoles, can attract one another. And so the positive end of one water molecule, which are the hydrogen end, is attracted to the negative end of another water molecule, which is the oxygen end. And so the hydrogen end is attracted to the oxygen end. That's what holds us together. But not all water molecules are going to have the same energy. Some are going to have enough energy, sufficient energy, to break off the surface of this droplet of water. It's probably one large spherical droplet of water evaporating. And so they break free. When they break free, you see, they've broken free here. That's called, what was that called again? It's called vaporization or evaporation. When the water molecules break free and go into the gaseous state, that's vaporization. But sometimes what can happen is these water molecules are somewhat sticky, so a water molecule can come back in and get stuck. If a water molecule comes back in and gets stuck, what do we call that? Condensation. So evaporation or vaporization and condensation are continually occurring. It just depends on how humid it is. You know, if it's low humidity, that is, there's not much moisture out here, then we're going to have net evaporation. In fact, that whole droplet of water might evaporate completely. You know, if it's not enough to saturate the room. And so there are plenty of droplets of water here, but there's no way near enough to saturate the room. Okay, once we saturate the room, what that means is that the condensation, number of water molecules condensing, is equal to the number of molecules of evaporating and vaporizing. And when that happens, there's no net change. They call this a dimer. What dimer is two. So these are two molecules that are close enough they kind of attract each other electrically. But it's not permanent, you know, that's going to break apart. So sometimes the water molecules in the gaseous state get close enough to pair up, be a dimer. The water molecules, what are they doing? They're rotating, they're vibrating, and then they're translating. This is 97 degrees C. What happens to water at 100 degrees C? Boils. Let's see if they... Okay, it's pretty much been saturated, the air out here. It looks like the condensation rate is equal to the vaporization rate. Nucleation of water. Let's see if this molecular dynamic. So you got a sample of gaseous water there. If the air is saturated, then what can happen is, if it's saturated, then what can happen is it can condense into a little tiny droplet. And so this is the beginnings of a little baby droplet, like we call it nucleation. So we got to nucleate a drop, and as we nucleate a drop, then it begins to grow. So we have nucleation and growth into a bigger droplet as more and more water molecules condense on the surface. So here, there's a water that gets sucked in there and trapped. There. What holds the water molecules together? Yeah, intermolecular attractions. That's what holds them. Intermolecular attractions. These intermolecular attractions have varying degrees of strength, you know. Like, for example, maple syrup. Do you think maple syrup has strong attractions or weak attractions? Strong attraction. If something has strong attraction, is it more likely to vaporize or less likely to vaporize? Less. And so if we have strong attractions, do we expect a low vapor pressure or a high vapor pressure? So in other words, Does it vaporize easily, maple syrup? No. If it doesn't vaporize easily, then we aren't going to get very many vapor molecules into the gaseous state, which means it has a low vapor pressure. Versus something that vaporizes easily. What vaporizes easily? Alcohol. Like rubbing alcohol vaporizes easily. Does rubbing alcohol have high vapor pressure or low vapor pressure? High vapor pressure. It vaporizes very easily. We call it volatile. Things that vaporize easily are volatile. And they're going to generate high vapor pressures. And so for vapor pressure, there are two things that impact vapor pressure. One, the temperature. The higher the temperature, the more vapor. And two, the strength of intermolecular forces. The stronger the forces, the lower the vapor pressure, the weaker the forces, the higher the vapor pressure. So water has fairly strong intermolecular forces, so it doesn't generate. Whereas alcohol is going to have weaker intermolecular forces, so it's going to generate more vapor at the same temperature. Heat of vaporization. Heat of vaporization is the energy required to vaporize it. The energy required to break apart the molecules. The stronger the attractions, the more heat or the less heat required. The stronger the attractions, the more heat that's required to vaporize. And so the stronger the intermolecular attractive forces, the higher the heat of vaporization. Boiling point. The stronger the intermolecular attractive forces, the higher the boiling point, the more temperature it's going to take to boil it. So for example, maple syrup boils at a higher temperature than water. Water boils at a higher temperature than alcohol. Alcohol doesn't have that strong intermolecular attraction. Or as strong. The energy required to vaporize, again, is called the heat of vaporization. Heat of vaporization is given this symbol, delta H of vaporization. Delta H of vaporization is endothermic. It costs us energy to vaporize. However, when we condense, it's exothermic, it releases. And the interesting thing is it's equal and opposite. The amount of energy required to vaporize is the exact same as the amount of energy that's released when we condense. So one is called the heat of vaporization, the other is called the heat of condensation, and they're equal, except the sign is different. Okay, and then let me just finish off here with this. That is viscosity. Viscosity, the stronger the intermolecular forces, the more viscous. So maple syrup, is it more viscous or less viscous compared to alcohol? More viscous. Surface tension. Maple syrup, does it have a stronger surface or a weaker surface? Now what I mean by stronger surface and weaker surface is how much it takes to break the surface. Yeah, strong. So I'll give a demo for that next time. But I think what I'll do is I'll stop now for today.